right, so we'll finish up with vectors in space, which basically means vectors in 3D. So one thing we're going to kind of get away from a little bit is sketching. Okay, sketching in 3D is, it can be kind of tough to visualize things. So in 3D, okay, you have 3 axes. John's going to miss the picture. And your axes are x, y. Okay, that's like what you're used to before. And then z. Okay, that comes up off the plane. So the way that this is drawn, you kind of visualize like x, y is, this is like the corner of a box. It's the bottom. Okay, that's the flat part. And then z is like the back coming up. Okay, so there's your axes. Okay, and as far as describing it, there's really 2 ways you can draw a 3D coordinate system. Okay, the book describes this as a right-handed coordinate system. Okay, and the reason they do that is because they say, where do they describe it? If your index finger points in the direction of the x-axis, your middle finger points in the direction of the y-axis, then your thumb points in the direction of the z-axis. Okay? If you did that with your left hand, it would be the opposite. Okay, so if you take your left hand and have your index and middle finger both point the same way, your thumbs point in opposite directions. Okay, so this is called a right-handed coordinate system. It's kind of helpful sometimes if it's not drawn in a standard way and you've got to figure out which way is z. You just take your index and middle finger, point them in the directions of x and y, and your thumb tells you z. All right? So again, we're not going to be doing a lot of sketching, but that's the kind of system we're using. Okay? It's called a right-handed coordinate system. All right. So one thing we're going to do that we talked about very early on this year is how to find the distance between 2 points. Well, we're going to do exactly the same thing in 3D. Okay, we're going to find the distance between 2 points. Okay, for every formula I show you today, what I'm going to do first is put the 2D version, just to kind of get you to remember what that is. And then I'll show you the 3D version. Okay, so in 2D, you've got the difference in the x's squared, plus the difference in the y's squared, and then you take the square root. Does anybody have a guess what you're going to add to this formula to extend it to 3? Yeah, you're going to put the difference in the z's squared, okay? And then take the square root. Okay, so in 3D, first of all, I got to give you coordinates that are in 3D. So the coordinates that I give you will have an x value, a y value, and a z value. Okay, and finding the distance in 3D, it's a very, very simple extension. Still do the change, or the difference in the x's, square it, plus the difference in the y's and square it. And now you're going to add the difference in the z's, and then square it. Okay, so you add all that up, and then take the square root. So any questions on the distance formula in 3D? All right, so let's try it and then see what we got. I want to find the distance between those 2 points. So P1 has coordinates -1, 3, 2, and P2 has coordinates 4, -2, 5. All right, so Connor, what's going to be the first 2 things that I subtract?
4 minus -1.
Yep.
So it's going to be 4 plus 1.
Right, we'll do that in a second. So 4 minus -1, and then I have to square it. Plus. Okay. Skylar, what's going to be the next 2 things I subtract?
-2 minus 3.
Yep. Negative 2 minus 3. And what do we have to do with that?
Square it.
Yep, we're going to square it. And Jake, what about the last two things I subtract?
We take 2 and 5. Subtract 5 from 2.
Yep, 5 minus 2. Okay.
2 from 5.
And we also have to take that value and square it. Right. So now we just figure out what that is, and that's our distance between those 2 points. John, what's 4 minus negative 1?
5.
And then if you square it, 25. Okay. Brian, how about negative 2 minus 3?
That would be -5.
Yep. And if you square negative 5?
25.
25 again. Okay. And the last one, 5 minus 2 is 3. Squared gives me 9. So Katrina, what's going to be my distance here? The square root of 59. That's the exact distance between the 2 points. If they wanted a decimal, just type it in. It's about 7.68 units. In general, with these kind of problems, they don't give you a label like feet or inches. It's usually just a number like that. Okay. So any questions on that? Find the distance between 2 points. Now, did this have anything to do with a vector? What do you think? Did the problem say the word vector anywhere in it? No. Now, maybe this could represent an initial point and a terminal point, but just this problem itself doesn't really have anything to do with vectors, right? Just 2 points and you found the distance between them. Okay. Now, everything else will directly be what we did in 2D, and then I'll show you the formula in 3D. All right, so in 2D, okay, the way we could write a vector in unit vector form, we had A times I, and again, A would be a number, so it'd be like 3I. Then we had plus B times the unit vector J. And that would be something like 6J. Right? So 3I plus 6J. But now in 3D, we need one more unit vector. Okay? I allows us to move left and right. J, that gives you the vertical, the up and the down. What do you think the new unit vector I'm going to use is? K. All right, just to make it clear, I'll bold those, because those are vectors. All right, so in 3D, I is your movement along the x-axis, okay, which could be left and right. It depends. Now you're in 3D, so it depends on how you're looking at it. J is movement along the y-axis, and K is movement along the z-axis. Okay, so just like a coordinate in 3D, a vector in 3D has 3 parts to it. Okay, and if you were going to write it in our other notation, you could put the angle brackets, except now inside the brackets you don't just have 2 numbers. You have the x component, which is A, the y component, which is B, and now the z component, which is C. Okay, so any questions on that? Okay, very similar to 2D. If you make any one of these a negative, it just changes the direction. Okay? So if A was negative, that would be the negative direction on the x-axis. Okay? It could be left. It depends on how you're looking at it. Okay? Okay, so again, A, B, and C, those are the components of the vector. Okay, this definition you already have in your notes from earlier in the week. I'm just saying the same thing again. If you draw a vector that has its initial point at the origin, that's called a position vector. Okay, so you already have that in your notes. That's what it was called in 2D. It's still called that in 3D. Okay, any questions on that? All right, so let's take a look at how we find a position vector in 2D. To find a position vector in 2D, take the difference in the x's, comma, and then take the difference in the y's. What do you think I'm going to add to that to find a position vector in 3D? Yeah, I'm going to add, can you tell me specifically what I'm going to add, John? Yeah, I'm just going to do z2 minus z1. And that's going to be your last component inside those brackets. Now, does the order that you subtract them in make a difference? Does it matter if you do x2 minus x1 or x1 minus x2? Yeah, subtraction, it makes a difference. Do 5 minus 2 and then do 2 minus 5. You don't get the same thing. Okay, so the way you always subtract it is terminal minus initial. Terminal minus initial. Okay, so 3D, I've written down my initial point, x1, y1, z1. Terminal point, x2, y2, z2. And there's your position vector in 3D. Okay, so that's important. Right, so now I'll give you two coordinates. Okay, if I don't tell you which one is initial and terminal, always assume P1 is the initial. And then P2 comes second, so that's the terminal, comes after it. Okay, so bless you. Take a second, see if you can figure out the position vector for that initial and terminal point. Okay, and you don't have to write it with the IJK notation. You can put it just like I did up above. You should know how to do that, but you don't have to. Okay, so as I walked around, a lot of people, they got the right answer. If there was anything wrong, it's just because maybe you did the subtraction in the wrong order. So you're going to start out with 4 minus negative 1, then 6 minus 2, and finish with 2 minus 3. 4 minus negative 1, what do you get when you do that? 5. That's one that a couple people messed that up. 6 minus 2, that gives me 4. And 2 minus 3, John? Negative 1. Now, what if I asked for it with IJK? How would you write it that way?
5i.
Yep, 5i.
4j.
Plus or minus 4j? Plus, because it's a plus. Plus 4j.
Minus 1i. Just minus k.
Well, we already got the I. It's 5i
K.
plus 4j minus k. Could you put minus 1k, or is that wrong? You could, but you don't have to. All right. So now we're going to take a look at the same formula as we did in 2D. Okay, adding, subtracting, scaling, and finding the magnitude of a vector. Okay, I'm going to extend every formula to 3D. When we did it in 2D, if you wanted to add vectors together, you added the x components and you added the y components. In 3D, what else are you going to have to add? You're going to have to add the z components. So add the x's, add the y's, add the z's now. Okay, if you want to subtract, I just did it as part of the same formula. Subtract the x's, subtract the y's, subtract the z's. Anybody remember what you call this when you put a number in front of a vector? It was a something product. What does it do when you put a number in front of a vector? It can do a couple things. It It's a scalar product, right? Scale means you can scale things larger, or you can scale it down and make it smaller. Now, when we scaled, basically what it was almost like was a distributive property. You had to distribute that number. Okay, it could be like a 2 or 1/2. Distribute that to the x component. Distribute it to the y component. And what else do you have to distribute it to now? Z. Okay. Distribute it to the z. Okay, so there's your formula for scaling a vector in 3D. Just multiply each component by whatever that number is. Now, I said it can lengthen or shorten a vector, but it can also do one more thing. What else can happen when you do a scalar product? Would that shorten? Yeah, shorten or shrink, same thing. Anybody remember the third thing? It can change direction. How would it change direction with a scalar product? Yes, if you multiply it by like a -2, something like that. All right, so last formula. Okay. You already have that part in your notes from 2D. Okay, to find the magnitude of a vector, it's basically the Pythagorean theorem. Take the x component, square it, y component, square it, add them up and take the square root. What else am I going to have to put to do this in 3D? Plus or minus? Yeah, plus. Z1 squared. Okay, so this is basically the Pythagorean theorem in 3D. Square each component, add them up, and take the square root. Okay, so I don't know if we'll do one of each type of these, but we'll try a couple of them. Does everybody have the formulas?
Oh, yeah, I wasn't taking out yet.
All right, so I've got two vectors, v and w, and I want to add them up. Now, if we were doing this in 2D, one way we could do it visually is you draw them both, and then you line them up so the end of one and the beginning of the other connect, and then you draw the diagonal. But in 3D, you could do the same thing, but it's a lot harder to visualize on paper. If you've got a computer and you can draw 3D on the computer, then it's super easy to do. But we're just going to do it with arithmetic. Okay. So what would be my I component when I add these up? 5. 5i. How about the next component? Yep, it's 3 plus -4. You could put -1j, but you don't need to. And the k component? Plus 3k. Okay. If you were going to write it with the angle bracket, it would be 5, -1, 3. Either answer is correct if they don't say how to write it. Okay, let's find the magnitude of v. So to do that, you don't need w at all. Okay, so you don't even look at w.
So in 3D, we don't find the magnitude of W?
You can. This problem, I chose to do the magnitude of this one.
Okay.
Yeah. All right. So we're going to take 3 numbers. We're going to square them, add them up, and then take the square root. What's the first number that I square? 2. The second number? And the last number? -2. 2 squared gives me 4, and then 9 gives me, and then another 4. 17. Okay. So that's the distance, that's the length of that vector in 3D, square root 17. Is this answer a number or a vector? It's just a number. Okay. The answer that we got before is a vector. Okay. And let's take w and scale it. What does putting a 3 in front of w do? What do you mean multiply it by? What does that mean?
So the end product would multiply by 3. What you find out, you would multiply.
How would that look?
Would be, W times W. No, that's not.
I meant like visually, if I were to sketch W and then I sketch 3W, how would they compare?
They'd be bigger.
How much bigger?
3 times.
Yeah, this is going to take W and stretch it out 3 times as much. So take each component of W and triple it. Okay, so what's my I component? So 9I. And what comes next? J. And the K?
15K.
15K. Okay, so super easy to scale a vector in 3D. You just have one more number you have to multiply. That's it. All right, so dot product. If you could do the dot product in 2D, I could probably give you a problem without explaining anything, and you could do it in 3D. It's exactly the same thing. You just have to do one more step with it. So in 2D, what did we do with the x's for a dot product?
What?
How do you find a dot product in 2D?
You add them.
No, what do you do first?
Multiply them.
Multiply the x's, and then you're going to add, multiply the y's, and then add them. So now, in 3D, you're going to multiply the x's, plus multiply the y's, plus multiply the z's. So this is the extra step in 3D. Any questions on the dot product in 3D? Now because we're doing 3D, it's really important that you put in that dot. Not so much in 2D. I told you you should put it in. But why do I have to put that dot in? We talked about this yesterday. Yeah? Right, there's a different kind of multiplication you can do with vectors in 3D. You can either find a dot product, or you can do what's called a cross product. In 2D, cross product doesn't exist. But in 3D, it does. All right, so let's find the dot product between those two vectors. All right, so Marquise, what's going to be the first two things I multiply together?
5.
Yep, 2 and 5. Well, Brianna, the next two? -3 and 3, good. And Katrina, the last two? Sorry, 6 and? -1, thank you. All right, so we're going to multiply all that together, add it up, and see what we get. So we got 10 minus 9 minus 6. Dan, what's 10 plus -9? 1, and then 1 plus -6. -5. Okay, so that's our dot product in 3D. Any questions on that? Now, yesterday we didn't just find dot product. You got the dot product and then we used it to do what? What did we use the dot product for? Yeah, to find the angle. So we can find the angle between two vectors in 3D exactly the way we did it in 2D. In fact, the formula is exactly the same. There's no difference in the formula. Okay. The only difference is all the quantities are 3D. Yesterday you did a 2D dot product over a two-dimensional magnitude times another two-dimensional magnitude. Now you're doing a 3D dot product over a 3D magnitude times a 3D magnitude. But we've gone through how to do each one of those separate. That's what we just did. Okay, so what I'll do is we'll find an angle between two vectors, but we'll use the same two vectors we just found the dot product for. Then we've already done the first step in finding the angle. Okay, so let's find the, let me just double check that those are the same. We had 2, -3, 6. Yep, and 5, 3, -1. Okay. Okay, so to find the angle between them, you've got to find three things. Find the dot product, which we already know from the last example. Somebody remind me, what was the dot product we got in the last example? Negative what? -5, thank you. Now, we haven't found the length of u or the length of v. So we gotta find both of those. John, can you tell me how to find the length of vector u?
Um, 2 squared
Yep.
plus -3 squared, which is 9, plus 6 squared, which is 36.
36. Okay, and if we add up everything under the square root, what's 4 plus 9 plus 36? 49. And that's going to come out nice. What's the square root of 49? 7. Okay, so there's the length of u. And the last thing we need for our formula, if we want to get the angle, is the length of v. Okay, this one, I don't think it comes out as nice. We've got 25 plus 9 plus 1. So that's going to be the square root of 35. Okay, so now fill in the three things I just circled into that formula, and then we can get the angle between the two vectors. Cosine of my angle equals, okay, what goes on top? Yeah, -5. And then on bottom is the product of the other two numbers, 7. Now, if you did out what's on the right-hand side, that's not the angle, that's the cosine of it. So how do I get rid of cosine? Yeah, take the inverse cosine and inverse cosine. Okay, if you've got a scientific or graphing calculator, you can type all that in one step. You just have to use parentheses. As far as the mode, you could be in degrees or radians. I usually do it in degrees, unless the problem tells me not to. All right, so inverse cosine, -5 divided by 7, square root 35. Okay, type it in exactly like that. Okay. Might not need the extra set of parentheses, but if you put them in like I just did, it won't hurt anything. Okay, so the angle is about 96.9 degrees. Okay, any questions on that? And now that's a three-dimensional angle. So you'd have to imagine it's, it might not be something that's like flat on the board. Maybe something's coming off the board, right? And you're finding the angle between the two things, because it comes off the board. Right? So it's in 3D. All right. So the last thing we'll look at. We're not going to. I'm not going to do too much with it. I just want you to know the idea that I've been mentioning. Okay, the cross product. Okay, so the cross product is a second way to multiply two vectors. Like that star-crossed lovers cross product. Anyone catch that? Okay. So the cross product is a second way to multiply two vectors. only applies in 3D. Okay, you can't do it in 2D. It doesn't exist. Okay, and there's different applications for this in geometry and physics. And basically what the cross product does is if you take two vectors, okay, and you find a cross product between them, what it'll do is it'll give you a third vector that's perpendicular to both the other ones. So when you might want to do that is, like, let's say you had a computer system, like in an airplane or navigation, and it had to figure out which way was up. Well, if it can send out two vectors kind of in a horizontal plane, and it finds the cross product between them, that third vector would tell you what direction is up. Or if you do it the other way, it could also tell you which direction is down. Right, but that's one thing that's really different about a cross product. The answer is not a number. The answer is a vector. The answer is a vector. And specifically, as I just said, it's a vector perpendicular to both original vectors. The two vectors that you took the cross product of. Okay, and this is one time where multiplication is not commutative. If you, let's say you did V cross W, what that might do is give you a vector pointing up, perpendicular to both of these. If you switch it and do W cross V, you're still going to get a vector that's perpendicular, but it's going to be the other one going down. Okay? So switching the order you do a cross product in gives you a different answer. And as far as the calculation for a cross product, we're not going to get into it. It's not that hard, but it's just not something we're going to do. Okay? Hey, so any questions on just the concept? What a cross product is, or what the result of a cross product is? It's right there. Okay. Okay, so I think that's a good place to stop. All right, so the homework, you've got a little over 20 minutes. Probably get that done, because that's not really that many problems. I think it's only like 7 or 8 questions. 15, 17, 29 to 35 odd, and 41, 43, and 51. There's no word problems. It's basically just doing what we did in class, some extra examples.